Go ahead.
Okay. Hi all. I'm Michele Vanucci, and I'm presenting today this research that I'm doing with my supervisor Peter Bloom at the Vrije Universiteit here in Amsterdam. And feel free to interrupt me at any moment if you have any question, because we'll go through a lot of math, so you can interrupt me anytime. And to introduce myself a bit, I'm from Italy, but I'm now living in the Netherlands for my studies. And yeah, that's it about myself. I initially drafted a research proposal for the master thesis that was on a slightly different topic. It had to do with placing a discrete model as a cellular automata in the classic reinforcement learning feedback loop, or also the setting that is used for all the free energy related research, where you have a system that is interacting with the environment. So that system in that case would have been a cellular automata. But then with my supervisor, we pivoted that research quite a lot. The main thing that these two ideas share between each other is that the model that we use for the environment is discrete, because as we'll see here, we use a Turing machine to model the environment. And yeah, also this is kind of similar to a cellular automata, because it was demonstrated that some types of cellular automata are Turing, they can simulate a universal Turing machine. And also the other key idea that I share, like that this research shares with the original idea. Sorry, I said idea 3 times. Is that we analyze this agent through the lens of surprise minimization, which is prescribed by the free energy principle. And yeah, I think we can get into it. So this is the outline. I will first explain how this research connects to the free energy principle, because here we are basically assuming that the agent has a perfect can calculate a perfect posterior on the possible models of the environment, which is something that is not usually assumed in the free energy literature, where the external world is modeled with an internal state that cannot represent fully the external environment, of course. And so yeah, this is how we can decompose the surprise term as the free energy term here in blue, and the chiral divergence between the posterior given by the internal model and the true posterior P. And we can see here that if this divergence is 0, we are left with basically with surprise. So the free energy term equals surprise is this is why we say that we want to minimize surprise. And yeah, here I decompose it further. Now I developed the formula further just to show that this is the regular definition of free energy, but here instead of a continuous model class, we have a discrete model class that we will describe later more. So we don't have the the expectation is can be written as a summation over all models, over all possible models of the environment. Yeah, and this is how it's usually, I mean, this is how it can be written, the free energy. And we slightly changed the notation even further, but we will see this later. And yeah, we assume that the hidden states of the world are included in our model class, and they are static in a sense. In fact, the agent will try to model the entirety of the world, not just a part of it. And yeah, we'll see later how this is made possible. And yeah, and again, the posterior of the agent and the true posterior are equal. So we assume that the agent can do perfect Bayesian inference, which is of course intractable in the practical sense, but yeah, we stick to the theoretical part and see what it means for this kind of agent to minimize surprise. In fact, we will be using as our predictor the Solomonoff predictor, which is used in the AIXI setting. Yeah, maybe I should have introduced that what we are trying to do in summary here is that we give to an AIXI agent that is an agent that can that has basically unlimited computational resources the goal of surprise minimization, and we see what this means for this agent. The motivation behind this is that it allows us to disentangle the goal of the agent from its limitations, because here we assume that the agent has no computational limitations, and see what this kind of code would mean for such an agent. And now I mentioned that the AIXI agent uses the Solomonoff predictor to model to predict the next observation. And I'm asking the audience if anyone has heard about this, about the Solomonoff induction, and how much in detail do I have to go into it to?
Michele, usually our setup is that you are presenting and then the audience contributes towards the end.
Okay.
And you can, I suppose, assume to give us just the minimal we need to understand this, and you respecting the time limits.
Okay.
Estimation is yours.
Okay. So yeah, I assume that few people already know about this, so I will give a brief explanation about the Solomonoff predictor. So here is a bit of notation. We rewrite the prior with a W, which means weight, and our model new is just one of the possible models in the class. We already saw this new here in the summation. And can you see my pointer?
Yes, we can.
Okay. And yeah, we have this prior is based on the Kolmogorov complexity of the model. So simpler models will have a bigger prior. In fact, if this k term here would be 1, the prior weight of such of an environment with only 1 bit of description length would be 1/2 of the total prior, which sums to 1. And here we define the history as a sequence of actions and observations in different interaction cycles. And the posterior is rewritten as this. Similarly to the prior, we use the W letter. And here I just use this notation to be consistent with AIXI literature. And the likelihood of a given model is written in a slightly more compact way like this. And then we have that Solomonoff predictor is defined as such. It's basically a Bayesian mixture of all possible models weighted by their posterior, of course, how one would expect. And the key aspect is that these models that the Solomonoff predictor considers are Turing machines that we can represent in this fashion with an output tape and a head, which writes the new observation based on a program that is also the program that gives us the Kolmogorov complexity of the model. In fact, the length of this program will be basically the complexity of our model. So if we have a longer program, that model will be weighted much less, as we see here from the prior, which is exponential, meaning that it decreases by a factor of 2 for every additional bit in the description length. And yeah, here the program uses the next action to generate the next observation, and it writes that on a tape. And this Turing machine has also additional work tapes, but I didn't draw them here to didn't clutter the slide too much. And so yeah, here the model class is all computable environments. So the key assumption is that the environment is can be computed by a Turing machine, which means there exists a program that can simulate the environment. And this is a pretty weak assumption, let's say. And it's also the main assumption of artificial intelligence in general, because we assume that the environment can be modeled with a program, in short. And yeah, the motivation behind this prior is Occam's razor principle, which in short states that the theories with the shorter description should be preferred. Usually this is used in the context of science when you have to considering two different theories that can explain the same phenomenon, but if one is much simpler, then you would, of course, prefer the one that is simpler. And at the same time, since we are considering all possible Turing machines, we are not excluding any possibility, let's say. So we also, this is also coherent with the Epicurus principle of indifference, which means that all consistent hypotheses should be considered, at least, even though a very long program would have little weight. And yeah, then what AIXI does is it uses this predictor to predict the next observation, and this is then used to basically consider every possible action sequence in a brute force manner. And once every action sequence is considered, then the one that leads to highest rewarding expectations will be taken. And then this expectation is updated with every new observation, because the Solomonoff predictor gets a new information. So also in this sense, this model is uncomputable because it considers every possible action sequence and every possible future and every possible model. So this, but this gives us very important bounds, which I won't go over here, but they prove us that this model can maximize the reward with the little information that it has, and can do that in a Pareto optimal way with respect to any other possible policy. So how is the previous research in AIXI with intrinsic motivation as reward, you might ask? And my answer is that there is little research in this field. In fact, the only agent that was considered is the knowledge-seeking agent, which is basically the opposite of the kind of agent that we will be talking about today. In fact, this agent has as goal to maximize information gain in the stochastic setting, or to maximize surprise or Shannon entropy in the deterministic setting. And the reasoning behind this agent is that it would eventually allow the Solomonoff predictor to learn anything about the true environment, as we'll see. So here reward is defined as information gain over the next interaction cycle. And yeah, information gain is defined as the chiral divergence of the past posterior with respect to the future posterior, updated with the new interaction cycle that is noted with HT. And yeah, this gives some strong results for this agent. In fact, the main finding of the knowledge-seeking agent literature is that this formula tried to summarize it. These formulas tries to summarize it, but it basically says that the agent will eventually learn anything about the true environment, which is here noted with mu. And if we simplify it a bit further, we see that, yeah, this is we consider a history of increasing length. And we take the limit of that, so we can account for more information that the agent could squeeze out of the environment with time. And the history is also sampled from the true environment, of course. And with pi star, we refer to the policy of the knowledge-seeking agent. And this is the off-policy divergence of the Solomonoff predictor and the true environment under any policy that could be different from the one that the KSA agent has followed so far. Which this means that the agent could consider any possible other policy and would still predict perfectly the outcome, because it will have a perfect knowledge of the true environment. And this is possible because what this agent does is it tries everything. It tries every possible combination of actions, basically, to induce the surprising information, and which in turns increases the knowledge of the true environment. And yeah, so it will squeeze any information out of the environment that it can. But yeah, here I specify what this P means, but if you have any question, I can answer them later. So now we might have a question. So what's the problem with this agent? Like, this seems already perfectly working. This agent can learn the true environment, and the author also conjectures that it would learn it in the fastest way possible, even though I don't really agree. But the main problem is that the agent would surely die if that is a possible event in its environment. This was proven with this paper, and it basically demonstrates that since the agent tries everything, and with each new action cannot know with certainty, like, of course, the outcome, even if it has a perfect predictor, because it wouldn't have gathered enough knowledge to know that outcome. And so at some point it would encounter a situation in which not knowing the outcome would result in death. And this is also incentivized by the fact that the agent seeks surprising information, so it would try also the most extreme actions just to get some new information out of it. And it would also be yeah, it would also be overly optimistic for this reason. So what we do is that we we basically define the symmetric with respect to this agent, while the knowledge-seeking agent was maximizing surprise. For this agent, we try to minimize it, and this is of course inspired by the free energy literature and other few researchers in reinforcement learning, which talk about surprise minimization, even though it's not really explored that much in the reinforcement learning literature. And so we thought that it could be interesting to explore it in this setting, which is still reinforcement learning setting, but we use the AIXI agent which doesn't have any computational bounds. It's just a theoretical concept. And for now, we'll consider reward as a quantity to be minimized, just for simplicity, and we define it as like this, as the negative log of the prediction on the new observation at time t. Alternatively, we can also include the uncertainty over actions, which is something that is usually done in free energy literature, meaning that we also consider the free energy of actions. But within this research, I found that this doesn't change the behavior of the agent that much when we use these Turing machines as our models. And so the value then, which is again minimized, becomes the expected surprise over future trajectories. So here we have the policy, and here we specify the environment that we are currently in on the left, and the predictor used that will give us the surprise of the next observation. And yeah, this here I pointed at it. And yeah, we have the discounting part in the formula, because we can also introduce discounting if we want to give a certain horizon to our agent, which is usually fundamental in the AIXI setting. And here is the expectation part. We are just summing the probability of all possible futures. And here's the surprise parts. And this expected surprise can be decomposed with information gain and risk. And yeah, with this formula, we already see that if we are minimizing surprise, we are also, in a sense, minimizing information gain and risk. But since we assume deterministic Turing machines, this risk term will be 0. And this entails that our agent is minimizing information gain, which is exactly the opposite of what a knowledge-seeking agent would do. Furthermore, if we, instead of a fixed, instead of a discount, yeah, we set a fixed discount of 1 up to horizon m, and we use the same predictor as the environment, then we have that the expected surprise is just the entropy over future trajectories. I mean, this is already yeah, this is already known fact, and we get a cross entropy if those are different. And this is just useful to rewrite the value in a more compact manner. And yeah, here we see it again, and this is different from the value function that we saw before, because we have the surprise is taken over the whole trajectories, the whole trajectory. Here with O, we consider all the observations up to time t, and with O prime, we consider the future observations. And yeah, H prime is the future history. And yeah, if we change the reward to also consider the uncertainty over action, only this log term would change, of course. And here this conditional distribution is defined like this. So this
I feel like
this formula can be written in this fashion by aggregating all the surprises of all the observation because of the properties of the logarithm that allows us to multiply together the terms that are summed. And so since in the regular definition of the value, we take the surprise over only the single information when we sum up all the contribution over all time steps, then these terms can be aggregated in this model. And yeah, this is again what we saw earlier. So under the true environment and deterministic policy, we can also rewrite value like this. Here we just have rewritten the value as cross entropy that we talked about earlier. Here we then decompose the Solomonoff predictor as using the definition, which is the Bayesian mixture over different models weighted by their prior. And then, since both the environment and the policy are deterministic, from this summation, only one possible future will have a contribution of 1, which means we'll have this probability value at 1, while all the other possible future will be at 0, since both the policy and the environment here are deterministic. So we will only select the futures that are possible under the true environment and the given policy. And at the same time, this will select all the models that are consistent with that future. So we could have different models that under the same policy give the same observations. So yeah, this then can be rewritten as a summation over the priors of all consistent models, and with a given policy and true environment over an horizon n. And yeah, we just rewrite it in this manner to make it more compact. And yeah, this gives us a precise ordering of different policies, which means that the agent will try to keep the biggest part of the environment that has already in its prior consistent with the new observations. And these environments are, of course, weighted by their complexity. And so, for example, if there is a single environment who has who's very simple and can fit with the policy, then and all the other environments which are far way more complex also do fit with another policy, we will give priority to the simple environment because it has a much bigger contribution to the final value of our agent. And another key definition that we will use is of a niche, which is just defined as an environment that has a smaller complexity than the true one, but still it can model all its observations with a given policy. So we say that a deterministic environment is a pi niche of an environment, of the true environment mu, if it has a lower complexity than mu and gives the same observation under this policy pi. Yeah, this is the formal definition, but maybe you understood the sense of it. And to give some more intuition, we can look at this drawing. We have that here the true environment has been drawn in green, and we see that also these two environments in yellow and blue, mu and mu prime and mu second, they also fit with the true environment, at least in this section. And so that the agent would likely try to stay in this part of the environment and would go in a circle, let's say, to maintain consistency between all these environments. And we can assume that, for example, this environment mu prime has a smaller complexity and this mu second has a higher complexity. And yeah, since we want to keep mu prime in our prior, the agent would never explore and go, for example, this way, even though it could, because it would like to maintain this simpler environment in its yeah, it's in model, it's in its model class. And yeah, but one important thing to know is that simple environments aren't necessarily simple. This means that even though they have a low Kolmogorov complexity, they could also still be quite complicated, and this is our simplification. First of all, because the environments aren't Markov or they're not representable as a grid word because they are Turing machines, of course, so the environments can be any type of environment that you could think of. And we could also have a simple environment, like we could have this blue environment that could actually entail exploration if it would match with the true environment, let's say. But in general, let's say that this agent would seek some kind of subsection of its environments that in which it can, like, yeah, it would seek a certain comfort zone, let's say, in which that is consistent with the most number of models in its prior. but at the same time, also going in a circle is discarding those environments where the circle is, let's say, closed at some point in time. But this have vanishing weight if their complexity is higher than the environment, which is simply represented as this circle. Yeah, so in which case would the agent leave this niche and go explore more? In the case where this exploration would mean having more environments that fit with another a bigger subsection of this environment, let's say, and yeah, it's this is quite improbable, let's say, because we would need to have more environments with a bigger complexity and therefore lower weight, which all fit together, and they all jointly have a bigger weight than the policy, than the complex environments kept by the policy, which stays in this circle. So here I try to explain this formally. So if we have a policy that we call pi, which discards this, which is the simplest model we could technically fit the environment under any given policy, and we have pi prime that doesn't, then pi the total sum of the weights of the models kept consistent to pi should be bigger than the sum of the weights of the models kept consistent by pi prime, and this is improbable because this term has both can consider both a more complex model, but also the models that are simple as k prime. And this happens with decreasing probability with smaller k prime, which is the complexity of the simplest niche. Forgot to mention. And yeah, so this is just to say that this agent would rarely go on a tangent, let's say, but yeah, also yeah, this is our oversimplification because again, also simpler environment can force the agent to go in some other direction if this environment has a changing structure, let's say. So since it's a Turing machine, it could at some point decide that it will not give the same observations if the agent keeps going in this direction, but it would, for example, open this wall, and so also under that environment, the agent could go in some other direction. And yeah, and yet we have that the value given by the optimal policy is considering model the model as the Solomonoff predictor as the predictor as the Solomonoff predictor. And yeah, we will still have that the information gain on every environment is weighted by their prior, and this has a big influence, especially because the prior is exponential, meaning that yeah, meaning that simpler environments have a bigger role in the total result of the expected surprise. And they even though they are limited by the complexity of the environment, like the information gain that you could get in that single environment, here again where we see the prior is exponential, and we also take into account that the history is still sampled from mu, so this will actually be the expected value at time t. Here is the expected value at time 0. This epsilon is just a way to say that the history is empty. And if it's not, and we have a history up to time t, then the history is sampled from the true environment, but the future is predicted by the Solomonoff predictor. And in this case, the simpler environments will have a bigger weight because the Solomonoff predictor doesn't know the true environment, and it only knows that some of the simpler environments are still consistent with the true environment, which means that they haven't been discarded by the history. And so it will use those to assume that it's in a simple environment, and in that simple environment, which we call U prime again, we have that the value given by this environment, the contribution to the value it's always bigger than the contribution to the value given by all the other more complex environments, but still the jointly contribution of all the more complex environment mu second could be bigger, but again, this is improbable because they would also have to fit with each other. And yeah, so in short, what this agent would do is if it had knowledge of the true environment, it would just find a niche that fits with a simple environment it's prior. And how hard is it to do? It depends on the complexity of the true environment. And for example, we could have an environment that is not compressible by a simpler environment under any policy. And this is possible if, for example, we have a small action space so that the policy cannot compress the environment that much, and a small and also a small observation space. And yeah, so we could say that the dimensionality of the observation space and the action space as deeply tied to the possibility of the agent to actually find a more simple environment than the true environment, let's say. Because if it cannot find a simpler environment, then it would would eventually also get to know the true environment as not exactly as the knowledge-seeking agent would do, but still the biggest weight would be on the true environment. And it would still have some weight on more complex environments. And that cannot be discarded. And the knowledge-seeking agent maybe would discard them, but I don't think this makes a big difference if the biggest weight is still on the true environment. So yeah, here I just wanted to say that if we consider this ordering of complexities, meaning the mu prime is simpler, let's say, than the true environment, and the mu second is more complex, then yeah, their contribution is ordered in this fashion with any possible history. And yeah, here we are left with some discussion, which is mentioning the darkroom problem, which means, yeah, we could have, in fact, that the agent goes, as we've seen, in a circle, and this could be interpreted as unintelligent behavior. But at the same time, it would be the best behavior for the agent if to stay in this dark room if this this area, like if this external part of the world contains uncertainties and possibility of death. And the agent would have to experience some kind of issue of some kind of new observation from possible harms to go out of this circle. We could say that we could think of as a human, as a primitive human that learns how to and wants to explore how fire works, for example, only when it gets hurt from fire. And before, he wouldn't really consider fire as something useful. And if it doesn't receive any signal from the fire, that it could be useful, of course. And so yeah, I think then we could also say that we could change the prior to encourage exploration. And yeah, this could be something. For example, we could give bigger prior to more complex environments, and we could then want our agent to make those consistent with the true environment, and therefore explore more to um, discard simpler environments and keep those more complex consistent. But also at the same time, this wouldn't really work, because it could also find a simpler niche of those more complex environments that have a bigger weight, and stay in that if that niche is consistent with all the more complex environments. And also changing the prior would kind of defeat the whole purpose of the Solomonoff, no, sorry, the Solomonoff prior, which follows Occam's principle. And yeah, I would maybe interact with the capabilities of the Solomonoff predictors to learn quickly. And yeah, also we can't really increase the prior on certain information, for example, to model hunger, because here the prior is only on models rather than observations or actions. Yeah, maybe we could introduce it by making the model more complex. We could also think of giving a bigger prior to those environments where the agent gets to have food or do all the necessary things to survive. But also those environments would immediately be discarded if the agent, for example, doesn't eat once, and or because it would make those environments where the agent does eat and stuff inconsistent. Another thing that we could mention to address the darkroom problem is that we could assume that the word is interesting in a sense that it cannot be modeled by a simpler environment. This would mean that our board is not static, that you couldn't really have this kind of niche. And we already mentioned that this is also made possible by changing the dimensionality of the action of the observation space. And so yeah, that could be one way of solving the problem. We could say that this environment, which here is present as a grid word, but in reality it could be more complex and could be always evolving, and therefore there could not be a static niche that could model it. Maybe you could find one that it could model it at least temporarily, but as soon as the agent receives a signal that that niche is about to be disrupted, then it would look for new information to find a new and maybe a bigger niche that could be modeled in a similar fashion. And yeah, also one advantage of this model is that it's parsimonious in a sense that it discards the least amount of environments as possible. This could mean in a bounded approximation also having to compute less and to update the posterior less, which is the main source of computational burden for agentic models in general.
Michele, you're approaching 1 hour, just letting you know.
Oh,
wrap up
yeah.
in 1 minute.
Okay. And also, yeah, one thing is that learning is more stable because if the knowledge-seeking agent were to be implemented in practice, it would discard the most probable models first with the biggest prior, as opposite to what the surprise minimizing agent would do. And this would destabilize the learning a lot, since the simpler models have the biggest contribution to the predictive distribution. So yeah, this is some research from future work considering how this AIXI agent with this reward can be made computable, which is already done in general for the AIXI agent. There has been already some literature on computable approximation on it, but not in the context of intrinsic motivations as a reward, as a surprise minimization or knowledge maximization. So yeah, thank you. This is my email. And yeah, that's it.
Thank you, Michele. Let's all of us give Michele a round of applause for this very comprehensive presentation.
Thank you.
Now we open the floor for questions from our audience. please raise your hand. If there are any questions? If not, maybe I can answer some questions until people collect their thoughts. I think my questions mostly pertain to the first part of the presentation. And if I'm not mistaken, I think it's the slide just before the Solomonoff induction, which is slide 7, I think. That one, yeah, this progression. So I have mostly clarificatory questions, as some things are not clear to me. First, maybe I recall badly that the first equation is actually not a plus sign, but a minus sign between the two. Though I might be wrong on that. But what I'm most curious on understanding is, what's the move? Well, how can you justify equating the approximate posterior with the true posterior, given that you are interested in then later on playing with the free energy bounds and estimations? So I like, the moment you do this, you don't do variational inference anymore.
Yeah. Here we
Explain more that. Just
there is no because the reasoning behind variational inference is usually that there is a latent factor that can change its value in time, right? Like a hidden cause. But here this latent is not modeled directly, because we want to model the whole environment itself, like the whole program that defines the environment. So in that program, there is already how the dynamics of the environment work. Like there is already and so the posterior also is also calculated, like introducing a latent factor when you cannot when you cannot do the exact Bayesian inference, and this is usually due to computational constraints. But here we don't have computational constraints, so we can indeed compute the posterior. That's what the Solomonoff mixture does.
I see. Yes, maybe this is outside my expertise, so probably I don't get it because of that. And maybe my last question would be, can you explain once again why equating evidence here with the Solomonoff posterior, or what's this log psi mean? Like, how does this work and why?
Yeah, also one way to think about it is that here we are not exploring like how this could be implemented with variational inference. The important fact is that in variational inference, what we want to minimize, or like in the energy setting, what we want to minimize in the end is surprise. And so that's the goal of the agent. And then this is done using the Solomonoff predictor to calculate the surprise. So the next observation is predicted with the Solomonoff predictor. And yeah, that's it. Also, yeah, usually this variational posterior is computed when you have some parameters that you can tweak to learn the posterior in an approximate way. But in this case, we don't have, let's say, internal states, rather than the only states are the weights of different environments. And also one thing is that there is a direct link between no, nothing.
All right. Fine. Thank you. So, yeah. Are there any other questions from the audience? If not, one call, second call, third call, then I suspect it's Carl's turn.
Is it my turn now?
Surprisingly, this time, yes.
Thank you. And thank you for a very deep presentation. So
Mm.
just standing back from the presentation, I think that the best way that we can help is to encourage you to pursue this idea of joining the dots or linking the universal computational Solomonoff induction perspective to the free energy principle. I think that's a really interesting thing to do. It hasn't been done completely or properly previously, and I think if you can establish a formal link between Solomonoff induction and the free energy principle, that will be really useful. One has to acknowledge that there are fundamental differences between the starting points of Solomonoff induction and the free energy principle. And one obvious one, of course, is that Solomonoff induction starts with algorithmic complexity and has certain commitments in terms of unlimited computing resources and discrete world states and discrete policies, whereas the origins of the free energy principle are much more aligned with Feynman's path integral formulation on continuous state spaces with random fluctuations. So they have a very different lineage, and that sometimes causes difficulty in understanding one lineage, understanding the nomenclature and the terms, the notation of the other lineage. But if you can put them together in some way, that would be excellent. I did not fully understand the derivations because there are too many substitution of variables and simplifications. There are too many moving parts for me to follow. The free energy principle is much simpler than the notational complexity, ironically associated with the Solomonoff induction. But I did recognize a number of key ideas, which makes me hopeful that you may be in a position to link and relate the two fields. But I think you're going to have to do that because I'm too old to understand this algorithmic complexity approach, and I don't have time to do it. But you do have time, but it will require, I think, you having the same depth of understanding of the free energy principle as you clearly do of the Solomonoff approach. And when you do, I think you can very gracefully move between the two and show how you could leverage one in terms of the other. And I think one nice example of that is what you've tried to do here, which is to take from the free energy principle the imperative of surprise minimization and then apply it in the context of algorithmic complexity or the formulations that you get from this kind of universal computation. So that's a one very nice illustration of being able to link the two fields. Another obvious link here is the emphasis on information gain inherent in the knowledge-seeking formulations in the universal computation domain, and the importance of information gain in describing self-organization in continuous systems. As an overall comment, it seems to me that I may be wrong, so correct me if I'm wrong, but it seems to me that you've described to us um, the sort of state-of-the-art universal computation under this sort of XI AI formulation. Is it Marcus Hutter formulation? Um, and then taken us into the world of knowledge seeking, where you make the reward function the information gain, and then say that that doesn't work very well. And then say, why don't we try surprise minimization? So we make the reward or the negative reward the self-information or the surprise, and then see what happens. And then what you found is that you have a dark room problem, that the agent will seek out comfortable, simple, minimally complex parts of the environment. So then you have to ask, well, how can I put the exploration back in again? And then we get to the solutions that you listed on the final slide, such as equipping the agent with certain priors, but we can't do that because that violates the Kolmogorov priors. We could have an interesting world um, prior and other devices that would basically put the information gain back in. Um, so my intuition is, in fact, you need both, and you need both the information gain and the surprise minimizing parts. And if you have both of those parts in, that would be formally isomorphic with the free energy principle. So the expected surprise you're talking about is the homologue of that in the free energy principle, which would be the sort of, I repeat, the continuous state space formulation that you can also write down for discrete state space models of the kind that you're dealing with, should you want to, would replace expected surprise with expected free energy. And the expected free energy is basically the expected information gain. Sorry, the negative expected free energy is the expected information gain minus the expected surprise, where surprise is just simply the negative log probability of an outcome. And I think that the resolution of the dark room problem is actually having a mixture of your surprise minimizing scheme with the knowledge seeking scheme. And mathematically, I think that will actually be a proper surprise minimizing scheme. I may be wrong, but what I think you've done is you've over-interpreted surprise. First of all, as noted by Robert, you've associated the self-information or the negative log probability of an outcome with a Solomonoff predictor. So that's actually a probability of a random variable. It's not the actual observation. And then later on, when you were taking us through the construction of the surprise minimizing agent, it seemed as if you were equating the surprise with the predicted posterior of an observation given H, or given the history of the actions and observations. That's not the surprise that the free energy principle minimizes. That would be in expectation and ambiguity. So I think that the resolution to your problem, the dark room problem that you presented at the end, and all the worries about the little agent going around in circles and not exploring in the natural kind of way, could be resolved by thinking carefully what surprise are you trying to minimize, and then if you unpack that expected surprise, you should get back the um, the information gain, which at the moment you're minimizing, which is I think why you have a dark room problem, um, um, and the the constraints that basically stop the agent being burned. If you remember that nice notion of curiosity killed the cat. So that particular problem is resolved by the expected free energy having two parts. It's got the information gain part, but it's also got the cost part, which is a negative reward, which stops you getting burned. So that's the kind of surprise that is referred to in the free energy principle. It's just how unlikely is it that I will be burned? So if I get a burning outcome, that to me is just very surprising. So it's nothing to do with prediction. It's just the surprise of being burned. And that's a constraint that is added to or a log constraint that is added to the expected information gain. And then those two together now become the expected free energy, which I think is your expected surprise. Um, I appreciate this may make no sense to you whatsoever, but I am aware it's being recorded, I fondly hope, so that you can go back and think, oh, I understand. Oh, I think that's rubbish, but I'll just make sure. I'll try and take you through what I mean by these things. And if you can make sense of what I'm saying, I think that you could tell a very compelling and important story about the links between augmented Solomonoff induction schemes that have knowledge seeking in them under constraints and the free energy principle, which would be much more straightforward and would also, on the one hand, resolve your problem, the dark room problem. But also interestingly, on the other hand, I'm just mindful that you started motivating this universal computation style of theorizing by noting that although it is incomputable and it's intractable, I appreciate that there are approximating software environments that you can use, but mathematically it cannot be realized because it's all it's not tractable because of the universal computation assumption. But what you also say is, but there are some really interesting bounds or limit cases that come out of the analysis. And that would be really interesting from the point of view of the free energy principle. If you could write down the free energy principle in this calculus and then rederive the bounds that would now apply to the free energy principle, that would also be, I think, a very useful contribution. Um, if you'll indulge me, I'm going to share my screen now and just take you through a couple of papers that I occurred to me during your presentation that your thesis usefully reference if just for
Yes, that would be nice. Thank you.
good. Now, where are we? Oh, there we are.
Yeah, also I think you summarized the content of my presentation pretty well. And yeah, maybe I don't understand fully how the free energy minimization can introduce the information gain.
Yes, it is not simple. And yeah,
Thing
that
is
was
that,
my
sorry,
carry on.
I looked at like the free energy term from the lens of variational inference, like the elbow, and so I didn't really, yeah, I read some free energy literature, but then I yeah, I stick to the variational inference perspective, which is which is basically like the evidence lower bound is like providing a bound on surprise, and it is done because well, we cannot compute the posterior perfectly, but yeah, I mean, in this case, we don't have any computational bound, so I just thought that I could just use what the elbow is trying to bound, which is surprise.
Yes, and actually, I think you can do that. So just speaking to Robert's question, I think you can ignore that variational gap or that variational bound in your analysis because you're looking at an idealized case where you're trying to derive
Yes.
you're trying to derive limits and bounds under idealized assumptions. So I'm glad that you said that you sort of adopted the sort of variational Bayes perspective on the free energy principle, because I think that's possibly the wrong focus. And I think that if you just stand back and understand the simplicity of the free energy principle, a lot of your assumptions will make much more sense. So, for example, the free energy principle, as derived under a pathological formulation in continuous state spaces. This has got nothing to do with Shannon-esque stuff. It's got nothing to do with Kolmogorov complexity. It's got nothing to do with Turing machines. It now deals with the random dynamical systems where the randomness is given by random fluctuations. So it's now all dealing with probability densities, not probability distributions over discrete things. If you start from there, then you can make the assumption, for example, and so this is the most recent description, which I think you will enjoy reading because it will, I think, help organize the motivation for various kinds of surprise minimization and explain where the information gain comes from. There are two key points to be made in this paper. Two key points I want to make to you that I'm using this paper to remind myself to make those points. One is that if you start from the physics of random dynamical systems, then you can assume that the internal states are performing exact Bayesian inference, which is exactly what you assumed on your first or your seventh slide. And that's perfectly okay. All you're saying is that in an idealized world, under idealized assumptions, I can associate, by definition, the internal states of any agent with the sufficient statistics over the posterior over the latent causes of my observable outcomes. That's exactly what is done in the physics version of the free energy principle. The second point is that all of the interesting stuff is about the agency. So all of your interesting observations are about the policies and policy optimization. And that means that what you're really talking about is not the variational free energy, which has the bound elbow aspect to it. You can ignore that. The really interesting part is the expected free energy. And that's your expected surprise. So what this paper does, the second reason I'm putting this paper up is that it derives your expected surprise, or the free energy principle's expected free energy from first principles. So this is not like, it doesn't make any assumptions like, the priors over the complexity, or it derives what would have to be the case in terms of sequential policy selection if something was self-organizing to a particular set of states. In this literature, this is called a pullback attractor, and the shape of this attractor is simply scored by the self-information or the negative log probability of any particular point in state space, and specifically the observation space being occupied. So this is something that's missing from universal computation. If you don't have reward, there is nothing to tell you about what are the characteristic states to which this agent will work towards. So if you put rewards in, that's one way of saying, oh, it's more likely that these agents will work towards these states or these outcomes, or will adopt these policies that lead to these outcomes that have a high probability or a low surprise. In the free energy principle, we don't use the word reward. All we talk about is the surprisal or the self-information or the negative log evidence of an outcome. So also known as a marginal likelihood because it's not conditioned upon the past or the future. It's not conditioned upon knowing the hidden states. It's just the marginal likelihood, marginalizing over everything, just saying, if I'm this kind of agent, then this outcome is very, very probable, and this outcome is very improbable and has a high surprise. So that's a surprise that's minimized in the free energy principle. How do you do that? Well, you behave in a way to minimize your expected free energy that has your kind of surprise, or technically in the visual search literature, it's called a Bayesian surprise, which is the information gain, but also the expected surprise, which is to stop you getting burned. So you basically have to specify the kind of agent you want in terms of the constraints on the states or the outcomes that that kind of agent would expect to encounter. So if you want to write down the mechanics of an agent that doesn't burn itself, you simply have to say that being burned is very surprising. And then you select your policies in order to the cross entropy or the expected surprise under some future or predicted posterior is now very costly, and that's the expected cost or the expected surprise. And that in combination with the expected information gain is the expected free energy, and anything that minimizes its surprise on average will minimize its expected free energy. So that's the basic story that I think it would be really useful if you could see the simplicity of that story, and then you can sort of choose or rename what you're talking about as expected surprise as expected free energy, and work out what's missing. And what's missing is two terms: one, the actual expected surprise, and an entropy term. And together, what you'll get back is something that has both the expected reward and the expected information gain, where now the expected reward is a free energy expected surprise. I'll try and explain how that goes, but as the reason I put this paper here is that there are no choices here. There are no assumptions. What I've just said is just a natural consequence of any system that self-organizes to an attracting set, where the attracting set is just scored in terms of the surprise or the self-information or the surprise associated with each state of being or each member of that state set, whether it's continuous or discrete. You can go through this at leisure, but the key result you're looking for is this result here, which is your expected surprise, free energy principle, expected free energy, that has all of these things in, including the risk ambiguity. This is the expected surprise, where I'm now using surprise in a free energy sense. It's just the Lagrangian, the self-information of some sensory observation that would be very surprising if I was the kind of thing that didn't get burned. And then we have our expected information gain. Yeah, I'm showing this first just to show, just to reiterate, the free energy principle is not an axiomatic theory. It's a first principles theory where you derive these expressions. You don't guess or choose. You are effectively just implementing a description of what it is to to effectively go around in circles like your little agent, in the sense that you're occupying a particular set of states, and that characterizes the kind of agent, that you are. But I repeat, from your point of view, the actual variational free energy bound you can ignore, which is good for you because you want to ignore it because you want to work with universal computation.
Yeah.
All the interesting stuff is in the expected surprise and the expected free energy, which is this here. This just assumes that the agent has an exact posterior over the current states, which means it can do its predictions into the future actions to get the history in the past and the future in exactly the way that you had. So that's that one. But what I just very quickly, yeah, by coincidence, we had a presentation from a Japanese colleague yesterday who did a wonderful presentation linking the free energy principle to things like rate distortion theory and with a nod to compression and algorithmic complexity. And I was reminded of Jürgen Schmidhuber's. So I think he worked with some of the originators of AIXI AI. Um, and has always impressed upon me anyway that this deep link between curiosity and compression and algorithmic complexity. So complexity minimization is compression, and he always has maintained that this is curiosity and this is just information seeking or knowledge seeking at some fundamental level. And he likes to tell people this. Do you know Jürgen Schmidhuber? Have you heard of him?
Yeah, I read a paper from him about curiosity, and also he would like motivate the interest in arts also, I
All
think.
right. Yes. Yes.
I don't know if you
And
recall.
fun, having fun and
Yeah,
creativity. Yes.
yeah,
Yeah. But I mean, he's been telling this story since 1990. There's a deep link between, I repeat, algorithmic complexity minimization, compression, and curiosity, which I think is quite nice. You've got the three C's there. It's just something that you might want to slip into the introduction of your thesis, just to say that there's an interesting, deep link between these things. Um, the other paper that I recovered for our colleague yesterday was that people have noticed these links in the past between algorithmic complexity and variational free energy minimization, reading variational free energy in a sort of Helmholtz or Feynman sense. And this was one example very early on by David McKay, who's quite a famous person in statistics and machine learning, just casting cryptanalysis under an algorithmic complexity frame as free energy minimization. So it's another little historical link between these two lineages or lines of thought that hopefully converge upon the same conclusion. But what I wanted to do was, I'm sure you've read this because I think this is probably the most relevant for your thesis. Because it's all about basically expected free energy on discrete state spaces, which in the limit will be deterministic, but should comply with the same rules or some assumptions that your work is about. And the reason I wanted to show was just to unpack the moving parts or the terms in the expected surprise, just just to see if these ring a bell with you, because when I went through your presentation, I saw little bits of the expressions saying, "Oh yes, that's right. Oh yes, that's very similar to the expected free energy in the free energy principle." So I'm not expecting you to give me an answer now, but I'm hoping that you'll be able to go through these decompositions of the expected free energy and say, "Oh yes, I was using that. Oh yes, that's what I can replace that with a Solomonoff predictor. Oh, that's a conditional entropy or an ambiguity term. Oh, that's what I meant by the expected surprise." And if you can do that, I think you can then draw the lines between or the links between the free energy principle um, as in the literature and the universal computation perspective or idealization of these things. So this is your traditional elbow-like formulation of the free energy, which is used to update your beliefs. You don't need to worry about that. You can assume that the agent has perfect beliefs, or an exact posterior. But if you didn't want to, this would be the mechanics of how do you get the closest approximation to the posterior, and the elbow perspective. Just to clarify, and for those people watching the recording, S here are states. They're latent states which are not directly observable, but they are the structure, of the cause-effect structure in the environment, that could correspond to your mu, to the things that are sampled from the space of models, for example. But in this formulation, it's slightly simpler. We're going to assume a particular model, and just worry about making inferences about states of the world. You can apply the same mechanics to the model itself if you want to, but for the actual structure of the problem, I'm just going to focus just on inferring the states of the world, because you haven't got complete observation of the world. So this is why you have partially observed problems. But I don't think it has any greater implications for the expected surprise or free energy up here. But for completeness, these are states. The pi is a policy, a sequential policy, a sequence of actions or a combination of actions in the future. And here is my elbow. So I can write this down as either a KL divergence between my approximate posterior and the true posterior, plus a surprise term, where the surprise here has been conditioned upon policies, but normally you don't need to, you wouldn't need to do that. And I can rearrange these terms into complexity and accuracy. And I think that's interesting for you because now you've got an alternative way of thinking about complexity. At the moment, you've been thinking about it in terms of algorithmic complexity. However, the same, if you like, aspect of any given Bayesian belief or parameterized posterior distribution can be expressed in terms of the KL divergence between your prior belief and your posterior belief. So it measures, so now we're talking about not the complexity of the model as such, but the complexity of your sense making, of your belief updating, in the sense that the more degrees of freedom you use up in providing an accurate account of the observations, the more complex. So the minimization of complexity that you were talking about, or the, if you like, the prior that you talked about Occam's principle and principles of indifference. That is an emergent property of free energy minimization. In fact, surprisal minimization generally, in the sense that if you interpret complexity as the degree to which I have to change my mind in order to provide an accurate account of the data. So accuracy is just the log probability of the observable O, given I knew what caused it, averaged under my beliefs about the causes. So the log evidence, or the log evidence is equal to accuracy minus complexity, or the negative log evidence, namely the variation free energy bound, is equal to complexity minus accuracy. So that may or may not be a useful footnote to your thesis, because it just provides another view of complexity that complements, that has the same, if you like, implies the same imperatives as the Kolmogorov complexity, or the prior over models or latent states that penalize large degrees of freedom, or big models, or models that that have too many parameters. You can score it in terms of a KL divergence. However, that's not terribly relevant for your thesis. You're much more interested in the expected surprise. And it turns out that if we take the expectation of these things, what we end up with is the expected complexity read as a KL divergence between a prior and a posterior becomes risk, where risk now is just the difference between what I a priori prefer in terms of my hidden states and what I think will happen if I pursue the policy. So again, it's a KL divergence that measures how far away am I from my preferred states, and my preferred states are simply not being burned. So I have to write down the reward in terms of a prior surprisal, in this instance over the states, but it can also be over the outcomes. Um, and then the expected accuracy becomes the ambiguity. And I think that's the kind of surprise that you were dealing with. And that's a very important kind of um, um, kind of surprise to minimize. You want to disambiguate. You want to move to parts of the environment where there's a lawful, unambiguous mapping between the states of the environment and your observations in this partially observed context. And furthermore, the ambiguity term, which I think is what you were you were associating with surprise, is a key component of the the expected information gain. Here it's labeled intrinsic value, but it's just the expected information gain, or sometimes called Bayesian surprise, um, sometimes called intrinsic motivation. But you can see that if I now take this term and put it put it over here and then rearrange, the ambiguity is an important part of this expected information gain. So what I'm saying is that the expected accuracy or inaccuracy becomes ambiguity. But interestingly, the expected surprise, the expected negative log evidence now becomes an expected value or a negative expected value or an expected cost. And this is the cost of being burned. This is the thing that killed the cat. It's not the curiosity, it's the acting in a way, choosing a policy that doesn't render very surprising outcomes highly unlikely. And then the bound term now becomes the information gain, and that is that is the expected information gain. It's basically the difference in my beliefs about the states of the world with and without the observations that I would get if I pursued policy pi. And then you can sort of rewrite that as a mutual information. So my
This value is this value is minimized or maximized?
no, this is maximized. Yeah, it's really interesting. So notice that because and I'll come to that in a second, but just say that this is basically what I wanted to convey to you, because I think if you can go through this formalism and related formalisms so you understand it in the same depth that you understand the Solomonoff induction, I think you'll be in a very good position now to make them meet in the middle and derive your bounds and inequalities that then you could apply to the expected free energy. And furthermore, you can tell Hutter and friends that a knowledge-seeking agent is not enough. That you can't, reward is not enough, and knowledge seeking is not enough. You have to have knowledge seeking under constraints to actually account for self-organized behavior, real agents. And from your point of view, that means that you now you now have your expected surprise. Oh, yeah, so expected surprise read as a free energy, and the information gain as part of your overall expected surprise. At the moment, you've just been dealing with this term, I think, which is good. And just to say that this term is usually motivated by the street lamp effect, which is the effect you see in psychology, where you only look for your lost keys underneath a street lamp because it's dark everywhere else. So the response to the dark room problem is to switch on the light because that now minimizes the ambiguity or minimizes the conditional entropy of the observables given their causes. So it's a really important term, but alone it won't do anything. It can either be added to the risk, so you avoid risk, or it can be absorbed into the information gain. But your question was really important. Yeah, this KL divergence now is maximized. So this KL divergence is minimized. So you're minimizing the the KL divergence between states of the world under a particular policy and those states that are characteristic of you, that you're basically your rewarding states. And that will be the risk term. You're minimizing that, but you're maximizing, because I'd have to switch to make this into a KL divergence. I'd have
You
to
have to
switch.
switch the signs, yeah.
Exactly. And therefore the sign changes, which should be evident in this expression here. So, it's this when the signs change now becomes a KL divergence between, well, it becomes the mutual information, or it becomes the information gain afforded by the policy that leads to these predicted outcomes. So this is the thing that I think you would use your Solomonoff predictor to predict. And then under that prediction, you can work out the information gain, but also you're also going to be predicting that outcome that will have a surprise, which will be the cost, which will stop the agent being burned. So if it likes to be running around in that circle, that's fine, because it expects itself to run around in that part of the environment. But it will also explore if you relax those constraints by an imprecise prior over the Solomonoff predictor. In this world, that's usually referred to as a sort of a posterior predictive density over or distribution over observations, entailed by these cues here. But another interesting response to your question, the signs flip, so that now you're maximizing this KL divergence, so you're maximizing information gain. That happens simply because the outcomes in the future become random variables. And outcomes in the future now that become random variables now form the support of the predictor, of the posterior predictive density. And so suddenly now this term jumps to the front and the sign switches, simply because now, unlike here, where the observations weren't random variables, we didn't have to infer them. Now they're random variables because they haven't occurred yet. So this comes back to Robert's original question, why are you associating the actual outcomes with the prediction of the outcomes, which is going to be a prediction over a random variable. And it is that very prediction here of things in the future that does switch the sign, and then you get the information gain. So if you can tell that story, as I say, I think it would be really useful on both sides of the theoretical approaches to these things.
Yeah, definitely. Now I'm using yeah, you mentioned that the surprise I define is a prediction, but I think I'm using like the exact surprise experienced by the Solomonoff predictor when a new experience occurs. And only, yeah, it becomes an expectation when you take the value, like when you take the fact that is in the future and you don't know the future observation, but once that happens, then that is the reward that the agent considers, like the actual surprise given by the observation.
Right.
In
It could be very close to this. Anyway, I will let you think about it, because as I say, I'm too old to understand the algorithmic complexity side of it, but hopefully you're young enough to understand this kind of formulation, which will require a bit of mental agility, because the notion of complexity is completely different in this world, but it serves the same purpose, I think, or hopefully. I'll stop sharing my screen now because I've exhausted everything useful that I have to say.
Thank you very much for all the suggestions. I will definitely read through the papers you suggested.
And thank you, Michele, once again, with a physical round of applause, hopefully. for your fantastic presentation.
Thank you.
And we definitely encourage you to check back with the link once you get the YouTube link and follow the conversation, the exposition by Carl and the papers, because that's how we all learn here. And yeah, we will keep you connected with the people in the extended group if you have any other questions. And that should be it.
Yeah. On my side, I will let you know when I finish my thesis and I have a final paper that I can share with you.
That would be
Okay.
most
You're welcome.
welcome. Thank you, everyone. So with that being said, we adjourn the meeting and see you at the next TMB session next week. Bye.
Thank
Yeah.
you.